Okay, I think we can go live. Uh, this week is the culmination of our discussion on link design. So we started our discussion on link design this week. Then after discussing a few case studies, we did a recap on dispersion and dispersion compensation. So there were those questions in week 6 that were out of syllabus now. Basically, all of them got discussed this week. So, so we talked about dispersion compensation thing fiber, and then after discussing link design, uh, dispersion compensation, and like a more detailed discussion on dispersion, we moved on to nonlinear effects in optical fibers. So that discussion will end middle of next week, which is like middle of week 10. I think some of you must have already watched it. And I think one small section is about one small section of the assignment is about this self-phase modulation and all. Brunt of the assignment is all about uh, link design. Question number 2 to 6. Those are like uh, those are where your understanding is being tested. If you don't understand anything, you can go through the worked out examples in the class again. So basic concepts are like these are the concepts. So uh, determined by our receiver sensitivity, we have to make sure that some amount of power is some minimum amount of power is received at the receiver end. So depending on your losses in the system and how much power you're transmitting, you will have to design a link so that at the receiver end there is like at least the receiver sensitivity amount of power. So that is basically the loss budget part of the link design. And for the rise time budget, we make sure that the system rise time is lower than what our OOK system calls for. So we consider each of the contributing systems as a um, first order system, and then we treat them as like cascaded filters. And from there, our main working formula is this: that the system rise time is related to all of the component contributions using this formula. And how we relate this RC time constants and bandwidth and rise time. These formulas are also like useful. You have to understand how we arrived at these numbers. I mean, this is the workhorse, I think. Then for non-return to zero format, you can use B/2 bandwidth also to detect a signal, and that was one of the new concepts. And for return to zero, we need like the full B bandwidth, the optical bandwidth that we are using. Electrical bandwidth has to be equal to optical bandwidth. Then system rise time has to be lower than what is determined by the bit rate we are sending. So So link design is basically based on these equations only. You have to make sure that you keep track of how much power is getting lost in each step. So, and if you have doubts, I think the worked out examples in the class are like helpful. You will see all of the concepts that are required. Then we went on for a discussion on dispersion and the beta 2 expression that was not introduced in week 6 that we introduced here. Basically beta we expand as a Taylor series expansion, and from there we get this beta 0, beta 1, beta 2, and beta 3. Up to beta 3 we consider. After that we can ignore the higher order terms. Then group index was briefly discussed. That is just related to group velocity, just relating C to group velocity. Then D and beta 2, how they are related, that was shown. Then there was a case study that we started for the link design, and then for the same system with multiple spans, multiple alphas, we designed the link using dispersion compensating fibers. And then we moved on to a bit of a detailed discussion about how dispersion distorts the shape of a pulse. So there were some complicated math. The key takeaway is that the transfer function of the system can be found out using this expression. You will also see this beta 3 ignored in a lot of cases when the first term is dominant. And if we know this transfer function, we can invert the dispersion that was accumulated. So basically for dispersion compensating fiber, these are the two equations. For narrowband systems, we mostly use this equation. For WDF systems or a little wideband, we discussed a example case where like this was the more suitable equation. Dispersion and dispersion slope. You have to take care. And then we briefly touched on why we don't use DCF in modern communication systems, all of its drawbacks and all. And digitally equalizing is not very difficult if we know the length of the fiber. So if we have time, we can show you some MATLAB codes and all also how this dispersion compensation is carried out. Then we started our discussion on nonlinear effects. This nonlinear polarization and how in optical fiber this chi3 is the dominant nonlinear effect. Chi2 is not present for silica due to its like molecular structure. Then refractive index is defined just like this, and expanding this epsilon using chi, we have this approximate expression that the refractive index is this the linear part and summed with this uh, nonlinear refractive index parameter. From there, you find uh, like the definition of beta. You can find uh, where this like these parameters come up, and I think like assignment is asking you to use these three equations in one question. Um, you're supposed to find what is the maximum rate of change of power, and from there you're supposed to comment about what is the maximum frequency change that can happen. And after a brief discussion, like briefly touching on soliton, like how dispersion and nonlinear effects can interact, that is where this week's content ended. The assignment is not too long, I think, but like it is asking like conceptual questions. You might have difficulty. So are there any doubts? We cannot give it like directly the solutions because these are uh, like graded assignments. But if you have smaller doubts, we can address them. I see a few people on YouTube, and so basically when the assignments are hard, the attendance goes up. Huh? There was this question about how this 125 gigahertz corresponds to 1 nanometer in the forum. So that is coming from this how small changes in f correspond to small changes in lambda. Uh, so what we are writing is this. But so what you're writing is this, but like if you're confused, you can also think of it as like for small changes in frequency and wavelength, we're using just differential calculus. So at lambda equal to 1550 nanometer, that is known. C is equal to 3 into 10 to the power meter per second. What we're saying is if delta lambda is 1 nanometer, what is delta F? So this will come out to be something like Did I make some mistake? So like this is how the conversions, these are the conversions you can do. I hope it's not like too confusing. On YouTube side, I see no questions, but there are like a couple of people there. Uh, are you finding difficulty in understanding the questions that are being asked in the assignment? That is all.
Sir, am I audible, sir?
Yeah, yeah.
Sir, input SNR in the question number 4, input SNR and the output SNR with OSNR. Were there any relation between OSNR input and output? I'm little bit confused.
You have to use the ETFA noise thing. You have to calculate. Wait, let me check. So this is basically all of the ETFA theory that you use. I can post the theory in this forum if you want.
It will be very helpful, sir.
But like it is asking you to do the like all of the math yourself.
Okay, sir. So you can upload it after the assignment completion also. No issue.
Okay, okay. But like you have to keep track of the signal to noise ratio and like keep track that signal got amplified by this much and all.
Okay, sir.
Otherwise, like only non-straightforward question was that Gaussian pulse thing, that there you find the maximum rate of change of power, and then like the question is asking you to just use this much, and L effective also you have to. Yeah. Like these are the only parts, but like you have to apply it to a Gaussian waveform. Otherwise, like if there are no more questions, YouTube side also I don't see questions, so we can close and you can use the forum. Wind up fast. Okay, we can leave.
Thank you, sir.